All right, so welcome to Module 8, Computational Chemistry for Experimentalists Lab Practical. Today we're going to learn how to compute the HOMO-LUMO gap, absorption energy, excited state geometry, and fluorescence energy and fluorescence shift of simple molecules. We're going to use ethylene as an illustration. You're going to use coumarin dyes in the actual lab practical. So let's jump to, I've made a remote desktop connection. I've set my environment variables, I've launched GaussView, and I've also prepared a spreadsheet to keep track of the level of theory and the energies and all the things that I need. Because I'm going to be converting from energies to absorption wavelengths, I'm going to need in this spreadsheet 8 Planck's constant, speed of light, Avogadro's number, and I've also got an experimental absorption wavelength of ethylene, which is about 180 nanometers. So, our first step, whenever we do these simulations, we always want to start with a decent ground state geometry. Especially if we're going to be looking at an excited state geometry, you want to start with a ground state geometry. So, I'm going to start by creating the molecule. I'm going to make a new molecule. It's going to be ethylene. I can use the R group tool to just grab a decent geometry of ethylene. And I'm going to start with geometry optimization. I'm going to look for a minimum. I'm going to use DFT with the default B3 lip function now. I'm going to use the 631G parentheses D basis set. I'm going to save for now all of my files in the documents folder. Clean opt. Submit the job. Because I've got my environment variables set up, I can just run this job no trouble. It's a relatively small molecule. I'll find and optimize geometry pretty quickly. And all of this should be review. Okay, calculation's done. I'm going to open the checkpoint file. Why not? There's my optimized geometry. I might want to record just a representative ground state carbon-carbon bond length, because that's likely to change in the excited state. Click on the two atoms, 1.33072. Of course, I would round that to about 1.33 if I was reporting it in a paper. That's in angstroms. Okay. Now the next step. I just want to check that the orbitals make sense. This is a different interface than the one we've looked at before. If you have all the environment variables set up right, it's easy enough to use this. We'll just do visualize these. Click on update. We're going to look at the two highlighted orbitals, which is the HOMO and the LUMO. The highest occupied orbital is a pi orbital. The lowest unoccupied orbital, not surprisingly, looks like a pi star orbital. These are the orbital energies in Hartree in this diagram. I could look them up in the log file as well, but I'm just going to use them from here. So, the HOMO energy in Hartree is minus 0.2667, 26667, that's all right. The LUMO energy is 0.01881. The HOMO-LUMO gap is just the LUMO energy minus the HOMO energy. still in Hartree. And I'm going to put here just a new row. Let's see, the conversion from Hartree to kilojoules per mole to 625.5 kilojoules per mole per Hartree. So I'm going to get the gap times this conversion factor. Okay, so now that's in units of kilojoules per mole. I can multiply it by 1,000. To get it in joules per mole. I divide it by 1 over mole, Avogadro's number, to get in joules, which is kilogram meters squared per second squared. Right? So that's the photon. So this is now also equal to the photon energy. So if I had a photon whose energy equaled the energy of the HOMO-LUMA gap, that photon's energy would be 1.2447 times 10 to the minus 18th joules. So a photon of wavelength lambda has energy E equals hc over lambda. That's a basic quantum mechanics thing. So lambda is going to be h times c over e. If you check out the unit conversions, kilogram meters squared per second squared in the denominator, kilogram meters squared per second times meters per second in the numerator. This ends up having units of meters. Please don't autocomplete, I hate it. Now I take this and multiply it by 10 to the 9th. And so I get a photon wavelength of about 159 nanometers. And I can always, just to make my life easier, just format that cell to round things to the nearest nanometer. Okay, so my HOMO-LUMA gap corresponds to a photon of wavelength 160 nanometers. The experimental absorbance peak is 180 nanometers. Now, let's go on and look at what's the computed excitation energy at the ground state geometry. That's a vertical excitation energy. So what's the vertical excitation energy of this molecule of ethylene? That vertical excitation energy is going to be an approximation of the absorbance wavelength. Now remember, we're only going to be looking at a pure electronic transition. In real life, you'd see vibronic transitions that are coupled to vibrational transitions. We could add all of that in later, and we could come up with the necessary Frank-Condon factors. If you really want to get into better reproduction of experiment, you need a more sophisticated theory to include all these other effects, but we're just going to ignore them for now. So what I'm going to focus on today is how do you do that calculation? Okay. There's our orbitals. Here's our computed ground state geometry. Now, the next thing I'm going to do is I'm going to compute the excitation energy at the ground state geometry. Okay. So I'm not going to optimize it right now. I'm just going to look at total energy, a single point calculation at this ground state optimized geometry. The method I'm going to use, now I have a new tab that we've never used before. Rather than doing ground state, I'm going to do TDSCF, time-dependent self-consistent field linear response, which is a fancy way of saying get the excitation energy. We're going to still do DFT, we're going to still do B3-LIP, we're going to use the same basis set. That's not required here, but it's going to be useful because we're going to do an excited state geometry optimization. So our excited state geometry optimization should use the same method and the same basis set as our ground state geometry optimization. Okay, now I'm going to submit this job, save a new input file, ethylene excited state. Submit the job to Gaussian. It takes a little extra time because I have to calculate the derivative of the orbitals with respect to an applied perturbation, with respect to an applied electric field. So it looks kind of like doing a correlated calculation. Excited state calculations look like doing correlated ground state calculations from the point of view of how much time it takes. And that's not precisely right, but that's a good hand-waving sense. And this one, pretty quick. So this is what we got. Our excited state geometry is the same as the ground state geometry. Go up here. Usually there's a UV vis that we can see there, but I guess not today. That's okay because we can just try and look at the log file in Gauss view. And if it doesn't show up nicely in Gauss view, we can just look at the text document. Okay, there we go. Log file gives me UV vis. And I get, look, this nice looking computed UV vis spectrum, which is really a single transition broadened out by this extra thing. So here's the peak. Here's a second peak. The second peak is modeled to be bigger than the first peak. But let's take a look at the log file to really understand this, because I have one at about 147 nanometers and one at about 135 nanometers, and let's see which of those we actually care about. Close all of these guys, and here's our excited state. I'm just going to open this file. And here's the log file from the excited state calculation. The way this works is I do a normal ground state calculation. I get my SCF done. I get my occupied and virtual orbitals and orbital energies. And then I do something that looks like what they call CI singles, excitation energies. And I go down and I go down and I go down and I get a list of computed excitation energies. The first one is orbital 7 to orbital 9 is the major figure. So this isn't really a HOMO to LUMO excitation, it's a HOMO to LUMO plus 1. But computed photon wavelength, 146.33 nanometers. Look at this. Oh, this one also has a very negligible intensity. And then the second one has a little higher intensity. And then the third one has a negligible intensity. So my first excitation, even though the intensity is a little low, the wavelength is 146 nanometers. So what do I see here? My HOMO-LUMO gap gave me a photon energy of 160 nanometers. Here, first excited state, 146 nanometers. Now, two things to see here. First, the excited state energy is generally going to be smaller than the HOMO-LUMO gap because you go up into the excited state and then the orbitals relax, and that orbital relaxation lowers the energy of the excited state. Real linear response excited state energies are generally going to be below the HOMO-LUMO gap. In this case also, that first excited state is even farther than before. It's even farther than before from experiment. But, I mean, of course, that's the optically allowed. If we look at the state that has a non-zero intensity, that's at 134 nanometers. Again, that's also a little off. There's probably some solvent effects and things like that there as well. Okay, now the next part. What about fluorescence? The last thing we're going to do is look at how do we compute a fluorescence spectrum. So we're going to do something similar to before. So I'm going to open my original excited state energy calculation. And I'm going to modify the calculation. Rather than doing job type energy, I'm going to do job type optimization. And this should, state of interest is going to be root equals 1. So here, I have to say, which state am I going to optimize? And I'm going to optimize the first computed excited state. I could optimize the second computed excited state if I believe the first one wasn't relevant to experiment, but I'm going to start with the first excited state. So now I see an optimized TD root equals 1, the method, the basis set, and so forth and so on. Make a new input file. I'm going to call this one ethylene ES opt. This calculation is going to take extra time because I have to do an excited state calculation at each new geometry, effectively. There's tricks you can do to speed it up, but they're not that tricky. So it's going to take some extra time to do an excited state geometry optimization. Now, let's talk physically about what we expect to happen here. In a hand-waving sense, you would expect that ethylene's first optically allowed excitation is going to look like a pi to pi star transition. So, in the ground state, your carbon-carbon, if we talk about things in a freshman chemistry sense, in the ground state, your carbon-carbon bond order is 2. In the excited state, because you occupy a pi, excite from a pi to a pi star orbital, your bond order is going to be 1, or because you'll have one bonding and one anti-bonding orbital optimized. So your bond order should be 1. So your carbon-carbon bond length should be longer in the excited state. As you optimize the geometry in the excited state, you should get a longer carbon-carbon bond length. So that's what we would expect. So we're going to put here the excited state carbon-carbon bond length. And I'm going to modify these to say what's the distance of that bond. And here what's the distance of that bond. It's going to be in angstroms again. Save that guy. And things are running, things are running, things are running. And we're also going to get the So what's going to be the excitation from the energy difference between the excited state and the ground state when we're in the excited state optimized geometry? This energy should be smaller than this energy. That's going to be a fluorescence shift. So I excite the molecule to an excited state, the geometry relaxes in the excited state, and then it goes back down to the ground state emitting a photon. The emitted photon should be redshifted relative to the absorbed photon. And that's the normal fluorescence. So it's running, it's running, it's running. We'll let it keep running. Now we might be in a situation here, because this is taking a little while, we might be in a situation where the excited state geometry optimization doesn't fully converge. And if that happens, it happens. I'm just going to go with the unconverged geometry for illustration purposes. But you can see that this is taking a long time. It's taking a lot longer than the original calculation. That's why I recommend when you do the homework, when you do the assignment for this, don't use DFT, don't use this large basis set. Use Hartree-Fock theory, which is going to be faster in a small 321G basis set. You'll see some systematic errors relative to experiment. All of your absorption energies and fluorescence energies will all be way too high relative to experiment, but hopefully it's enough to get the trend and get the difference between different molecules well enough to say, okay, how can I design a new fluorophore based on these simple calculations on an old fluorophore? Well, as this is, oh, okay, all done. It's optimized. Let's look at the log file. Oh, and look at that. Remember, we talked about how Gauss view just draws little sticks between atoms, and those little sticks don't necessarily correspond to bonds. But in this case, here's something kind of nice. In the ground state geometry, it draws two little sticks between the carbons because their distance is 1.33 angstroms. In the excited state, once I optimize the geometry, it draws one little stick. The bond is a lot longer. As we said, we did a pi to pi star excitation, and that weakened the carbon-carbon bond. So the carbon-carbon bond in the excited state is longer than in the ground state. So this is our fluorescent shift. So the bond length 1.56, 1.5695. Pretty significant change from 1.33 to 1.57. Now, what about the excited state energy, the excitation energy from the ground state to the first excited state when we're in this optimized geometry? Well, I can get that from the log file as well. Ethylene ESOP.log. That's the long log file, blah, 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 blah. But way down at the end, I have the final results at the excited state optimized geometry. Oh, just as an aside, you can look at things like how the charges and charge distribution change. Geometry is optimized. We go up, we go up, we go up. Here's our excitation energies. Excited state 1, 6.2226 eV, 199.25 nanometers. State. And this is what we get. Shift is going to be the difference between this number and this number. So we get a 53 nanometer fluorescence shift, a 53 nanometer red shift. At this level of theory, we predict that ethylene absorbs photons, wavelength 146 nanometers, and then when it fluoresces, it re-emits photons, wavelength 199 nanometers. Now again, we should be a little bit concerned that, okay, here the oscillator strength is pretty large, so this is definitely an optically allowed transition. Once we get up to that state and we let the system relax, it'll emit photons at this wavelength. And that is basically it. We're just scratching the surface of simulating these kinds of processes. We have to worry about things like singlet and triplet states and spin crossing and avoided crossings and the level of theory that we choose and all this other stuff. But this is enough to get started. So now we have a predicted fluorescence shift for this molecule. What we want to do is take your 7-hydroxycoumarin, compute this excited state to ground state photon wavelength, and then look for how modifications to redshift that number. And then that will be it.